And I haven't really uploaded any video, have I? So I'm going to upload the videos for the lectures, and I think that's all. We'll talk about the rest of the class, what to do with the projects, where are the deadlines and everything toward the end of the class. And I think I should be able to clear out most of your homework grades and review grade, which by default, if you're not you're not doing something weird on your review, you should get pretty much almost either full credit or close to full credit. So I can switch to PowerPoint. Nope, not this window. This one. All right, do you see my screen? Because Microsoft Teams is not okay. One thing I need to fix. I need to fix the year. And that was your kind of in-class exercise that we go through together for today's material. Interesting. It won't really allow me to share the screen that effectively. Okay, so you see my screen with the slides? Okay, perfect. So we will continue on into what we call multiprocessor. What we learned so far, first of all, how to build a processor, which is good, right? We can build something that can compute your data. Then we talk about the memory hierarchy, which kind of tackle the slowest part of your program, right? If you need to access your data, how would you ensure that your data access doesn't take as long as it would have been if you need to go all the way to DRAM? I can assure you that most of your data access, when you're actually running any program, because of TLB and caching, 90 to 95% of your program data access will be in the cache, which means that everything will be a lot faster, right? Unless you go into the realm of a huge graph application where a lot of accesses are irregular. Irregularity means that we don't have locality. There's no spatial locality. There's no temporal locality. And there are already a lot of work from the theory side on how to make most of the algorithm more regular, right? And one thing that I need to kind of stress out, right? In your algorithm class that you all have taken or are taking right now, you all talk about the big O notation at the beginning, right? This is like basic undergraduate material. You want to basically make the big O or the complexity of your algorithm as low as possible in terms of the order. O of n is better than O of n squared, better than polynomial time, better than exponential time, right? But still, there's quite a good chunk of work in algorithm as well to actually make sure your data locality is good. Because if you have an O of n algorithm, we never talk about that constant that multiplied to the n. And that factor can be amazingly high if you design an algorithm that randomly access data without any pattern, right? So these are one of the things that undergraduate level of algorithm, even with the most of the decent graduate algorithm class would talk about the memory access a little bit, right? But unless you go to like an more like advanced algorithm class where you need to actually dive into like what the paper in algorithm also talks about, then most of the time they'll be revolving around the compute complexity, which by this time you probably realize no one cares. Compute, add, multiply, those are like one cycle, right? If you compare this to memory, you already multiply things by hundreds, right? So that's another big angle that you need to care. So there was a processor design, there was a memory hierarchy part. Then there's a big topic back around, I would say around 2004, if I remember correctly, around 2004, there was this thing called Pentium 4. How many of you remember that processor? Pentium, Pentium 1, Pentium 2, Pentium 3, Pentium 4. And suddenly, Intel and AMD changed its course. They're like, okay, we can't go and clock your processor further and further anymore. Those things are single core. And suddenly they come up with this dual core processor and quad core processor, and then this core i3, i5, i7, and now i9, right? The reason behind that is they want to make sure you don't need a nuclear power plant to power your processor. Sorry for my cat, he is trying to walk on my keyboard again. To power your processor. So what they do is, instead of making the processor, one giant processor, bigger and bigger and bigger, now what they do is, well, let's make the processor the same size, but stamp out 2 copies of that, 4 copies of that, 8 copies of that, right? They come with certain issues, but they come with a lot of benefits. How many of you run a program, or like basically have a computer running multiple programs in parallel at any given time? Everyone, right? At least you will have kernel threads that will manage the running of your Windows machine, Mac OS, and Linux. Those actually already spawn many threads to do things like manage the driver, manage the file system, to whenever you need to access any files, it knows exactly where to go to on your hard drive. Those require a different set of programs, right? They require an actual processor to do some of this processing data processing. Then you might be running Chrome, right? Probably one of the most common applications that you're running on your desktop nowadays. Then you might be running right now Microsoft Teams in the background. You're trying to render the video, right? For some reason, the GPU is involved, the CPU is involved. Because you have more cores with the dual core, right? This is especially multi-processor. You can make the processor faster that way. More work get distributed across multiple processors instead of every single thread get queued up in one single processor. This typically give you better application performance because you reduce the number of applications that share one single processor. And as I said, making one processor faster is always good, but the faster it gets, the more power hungry it's going to get as well. We'll talk about power in the next lecture next week. But at some point, there was a plot, right? That okay, how much you need to actually supply, how much power you require to supply the machine, and if you keep clocking, this actually grow exponentially, which means that at some point you need a nuclear power plant, which is probably not good, not a good idea. So the solution is to add more core. One example is you can have 4 core, right? A typical mobile phone these days would have 4 core with laptop. The lower and lower tier laptop would have 4 core. Each one of them would have private version of its own L1 cache and the share L2 cache. And we will talk about what do they mean by having a private cache and what are the problems that the private cache brings. Then we'll talk, if you have multiprocessor, how you utilize it. They are kind of like two separate, not two separate, you can do this together, but the first idea is, well, we can run separate program, right? They don't share data. If you look at parallel programming, right? So for both of you that enroll in the parallel programming and compiler class, you realize that the 3 model, T3 paradigm of parallel programming, right? Data parallel, which is what the GPU is doing. Shared memory, which is what the CPU is typically doing. Things like pthreads, right? Whenever you use pthread, whenever you use threading, those are shared memory model. And then there's message passing, which is a more common in like IoT devices where you have to pass around messages. Cluster computing also use message passing. When you look at running each separate program in each processor, now you're talking about more like is analogous to the message passing model where you don't have shared data. There's no shared variable. There's the shared library that you can use. The shared library is more like the program share the library with the actual library code. And the other program also share that library code. Okay, so I'm not going to talk about that. That's kind of like you merge the two paradigms together-ish, right? But each program don't share data. You probably don't want to share the kernel data, for example, with the data inside Chrome. Chrome probably don't want to share the data to Microsoft team unless somehow Google and Microsoft talk to each other and say, hey, let's actually share data. If they do have to share data, they'll use something like message passing. The second idea is to have each thread in the same program running across multiple core. This is basically classic multi-threading, right? They have shared memory, they have multiple threads working on different tasks. Each task will modify its own private data and some of the shared data. Basically, when you want to write the results, you want to make sure you employ logs, you may want to make sure you employ things that would allow you to have a correct program. So these are some of the possible ways to utilize multiprocessor. Any questions so far? Okay, so these are key issues in multiprocessor. The first one is, well, I'll talk about the first and second one together because they are related. First one is we have a lot of shared resources. DRAM becomes shared. The shared cache becomes shared, right? So it means that one application can somehow occupy the majority of the resource for some reason. Maybe it has a really good cache locality, it's cache friendly, but it somehow needs 2 megabytes of cache. And let's say your system has 2 megabytes of cache. The likelihood is they will occupy most of the cache. Right? So that's bad for the other application that want to use the cache. So the multiprocessor topics inside architecture is on basically it involves around the fact that when you have shared resources, how would you share them? How would you design a policy to share these resources properly? How would you design a way to map your basically your threads, your data across all this processor and all this shared memory? Then we'll talk about data coherency. This is one of the big topic in computer science, especially in architecture, right? You want to make sure every data access is accessing the most updated version of the data, otherwise you have bugs, right? So inside the hardware, you also need to ensure data coherency. Basically, you want to make sure if you access a private cache, that should be the most updated version of that particular address. We'll talk about this issue in detail in a bit. How to ensure data consistency. What do I mean by that? Well, basically, I assume you use some social network, either Facebook, Instagram, and if you delete Facebook, you might have used it before, right? One thing that you would have realized is, let's say you post something and someone comments on the post that you put it on your newsfeed or on your wall. What you will see is you see series of comments and sorted by time. Data consistency means that you see the same order of what happened as everyone else, right? Otherwise, if you see a different order of things, it gets weird. How about this? Let's say you are sharing certain news, right? And for example, let's say we just seen the U.S. election, right, last week, where there's Donald Trump and Joe Biden trying to Donald Trump trying to get reelected. Joe Biden is trying to basically compete and get himself elected as a president for next year. So So basically, what can happen if you do not have data consistency is that, let's say I see this trend. I see that, okay, initially on the election day, Donald Trump was winning, the Republican Party was winning because there's a lot of people who go out and vote in person, right? But we all know that the mail-in voting will favor Democrats, the Joe Biden party, which means that as time go on, as they count votes, which means they count this mail-in ballots, right? Joe Biden will get more and more votes, and eventually he won, right? He actually won, legit, like square legit, which is good thing. They have democracy. Unlike Thailand, we don't have proper democracy, which is fucked up. But yeah, sorry about the swear word, but I don't like that fact. It means that what I see should be, okay, Trump was trending, he was winning because of the in-person voting, and then he was losing afterward after all the mail-in voting are counted. That should be the story that everyone sees. If you do not have data consistency, it means that these news can come at you in any order. It can be that, okay, somehow Biden was winning, and then Trump was winning, and then who know what happened, right? You need to ensure data consistency when you need to transfer the series of sequence on what happened to certain things. In this case, the US election is one of the most important events in the world, right? Because of their like one of the most powerful country, everyone should see the same sequence of what happened, who won the election, right? This means you need to ensure this data consistency. Ensuring this in the real world is not too bad because we look at time in minutes, in hours, in months, in days, right? So to be able to like transfer all this news within the day period of time, that's okay. It's not too hard. It can be hard with your Facebook, where you have a bunch of cluster around the globe. If you think about inside the hardware, inside DRAM, you are talking about nanosecond. You're talking about microsecond, right? So it means that two processors should see the same sequence of what's happening, but that's within the microsecond time window. It's within the nanosecond time windows. The more you can shrink the time windows, the better, because you can have the most recent update, recent sequences update of your data. It means you enable more performance. So your goal here is not just ensure data consistency, but to ensure it in the narrowest time window as possible. The last thing is you need to talk about how to schedule what to run, when, and at what core, right? This is more like an OS topic and system topic, but I'll give you one example, right? So TGGS has this cluster, or originally owned by the MESD program. This cluster actually has a lot of processing core, and don't ask me why don't we have our own server, because that's also another really screwed up thing about TGGS. I will critique them because I'm actually openly critique them right now and has been critiquing them for a year. We have a fully functioning computer engineering program without any server for you guys to run things. Lucas, for example, you just ran into the issue on your laptop. So I ended up basically would use some of my machines in the lab for you, right? But I'm still in the process. So this December, I'm hoping to be able to transfer that server over to the whole TGGS. But the story is, well, they hired this company that claim that they're claiming to be like the best in the Thailand. I don't want to name the company because I'm not sure if they're gonna do something with me or not, but I'm not happy with how they manage our cluster. How to schedule what to run is important. For example, our own cluster has 3 generation of machines, the super slow one. These are mostly for the students, so that you can run jobs that being assigned in the class because those are not like compute heavy. If you run your sample code, it wouldn't take more than a few minutes, right? So you can run these, you can run this job on a slow machine. That's fine. Then there's a next generation, which is slow, but it's not too bad. And then there's a newer one, which is also slow, but not too bad. So there are 3 speeds. The newest generation is the fastest one that most of the researchers are using. So the goal when you have these kind of clusters is you want to be able to separate the 3 cluster because if you have multi-threaded application, what do you learn about multi-threaded with barriers and synchronization? They are waiting for the slowest thread, right? They are waiting for the slowest thread to finish. Otherwise, the program never finish. That's your performance bottleneck. So if you somehow group the 3 machines together, your multi-threaded program will be as fast as a slow machine. That is a really, okay, I'll use this, that's really stupid way to run a cluster. So they charge us quite a lot of money per year, and this is what they got. And I'm like, I'm having urge to talk to the person who teach these guys, because I know who's teaching these guys, and basically critique him directly that this is so wrong. How can your student run a company this way? It's so bad. But yeah, so that's a story. We as a country are still not decent at scheduling these things. There's not enough people who know system, and now stop complaining. That's kind of like, how can this happen kind of events, right? So how can they be so incompetent? That's how I should put it. Basically, how to schedule what to run, when, and what call can impact performance quite a lot. All the lecturers who use the machine will they complain that they are slow. And these guys are not even be able to identify the bottleneck, which is also another like I'm dumbfounded by them, to be honest. Like they're so bad. Anyway, the last bullet point. If you take the IoT class, or if you are going to take the IoT class, I'm going to go into more detail. The last version of the IoT class, I don't have enough lecture slots to go into more details to talk about this. I'm hoping the next iteration of the IoT class, I actually will be assigned more slots, because I actually make a lot of noises in the meeting for the class, and I'm basically making sure that no stupid topics are being taught that are useless for you, that things that you can Google, right? So it's a master level class. So I want to make sure you get a proper level of things that you should learn about IoT. So this is one of the really important topic at IoT, because your hardware will look different. How to schedule what you run, when, and what core will be important. I'm gonna cover this toward the last lecture a little bit for this semester, but we don't have time to cover them all. This is really more about distributed computing, which is a class of its own, right? For architecture, we'll talk about the first 4 bullets, which are also equally important. The first one is managing interference. Interference means that I have 2 applications. One of them causes the other application to slow down. How many of you run 20 tabs of Chrome, and then you suddenly think your Windows is really slow? That's true, right? If you run 20, 30 tabs in Chrome, they'll use a lot of resources. They'll allocate memory, use your DRAM. And at some point, if you run out of memory, everything becomes super slow, right? So you have to manage resource when that happens. These are when you have multiple applications. Every single one of them want to use the main memory, because this is by default the interface between your running program and your processor, right? Your processor don't talk directly to your hard drive. They talk to the memory. The hard drive doesn't talk to your processor as well. They talk to the memory by transferring your program over, transferring your data over. So you want to make sure that you slice the memory up in the correct way for all the programs to run. Otherwise, some program will never get to run, right? Some applications are more demanding than others. Sorry, let me close the door. I think that's, yeah. Again, there's a really lot of dust today. So if you have PM 2.5 math or air purifier, please use it today. I actually saw my friends posting it's go up to like 120 or 140 today. So yeah, and I can feel it. I think my cats feel it too. It just walking. So basically, some applications are more demanding than others. Why? For example, if you have a really cache-friendly application, they use all the cache space, right? Because it's cache-friendly. Then they evict all the data. Okay, most my cats are in, so let me close the door and turn on the air filter. Sorry, I can't breathe so with these much dust. So when you have an application that are cache friendly, what will happen is they occupy the cache and they will run really fast. They're like, yeah, I'm happy. I have so much cache space. I'm gonna use them all. The other application, if you are not as cache friendly, but you have some hot data means I have a frequently accessed data, they're going to evict everyone else, right? So you're gonna run into a lot of thrashing. You remember the cache thrashing problem, right? Conflict mess cause things like thrashing where two applications use the cache and they happen to evict each other. No one wins. In this case, basically no one wins, right? Another thing that can happen, if you have one application with a really high row buffer hit rate, what the FRFCFS policy would do? Anyone want to answer that question? If I have an application with high row buffer hit rate, and when you have a processor, these days use FRCFS, so they will favor that application, which means that the scaler favor that application. Your other application never get to use DRAM. Is bad. So your application that are code running can slow down by not just twice, but 3 or 4 or 5 times. And the problem here is it means that load and store accessing your data takes even longer. And it becomes unpredictable to tell how long it would take if I have data access, right? If you only have one application, it's pretty easy to predict how long the access should take. In the worst case, when you have data access, it's going to be 15 nanosecond row buffer miss, right? But in this case, you don't know. You don't know how long because you have so many other applications coming in and out, right? When you have a computer, you don't just perpetually running the same 4 programs forever. Some programs get killed, some programs get initiated. So you have new programs coming in, old program getting killed, which means you have to manage it. You can manage it inside the cache. You will also should manage it inside DRAM, right? So let's talk about the cache first. By talk about how to handle cache interference. So cache is unique in a sense that this is hardware managed. So depending on how you write the program, each program got different benefit from using the cache, right? Adding n ways to an application. Let's say I have an application. I say, okay, I'm gonna guarantee you can access the 5-way inside my 8-way cache. I have 8-way. I'm gonna dedicate 5-way to my cache. I'll get certain benefits. Applications that are different will get different slope of that benefit. Some applications that are more friendly toward the cache, the slope will be really steep. You have a lot more performance gain as you increase more the amount of cache you give to that application. Applications that are not cache friendly, the slope will be really low. You give more cache, they don't care much. I mean, they benefit a little bit, but not much, right? So you need to be able to predict who wins more because you want to dedicate more cache to them. The next problem is this thing called performance cliff. What does performance cliff mean? Typically, performance cliffs means that if you plot performance on the y-axis, and x-axis can be whatever you want to investigate, the number of ways, which means the more cache space you're giving to that program. Performance cliff means they're going to improve performance, and then they'll plateau, and then they'll improve performance again and plateau. The reason behind that. So how many of you write program with nested loop? Nested loop is for loop inside for loop inside for loop. It happens, right? If you do matrix multiply, for example, you're going to have nested loop. The first cliff typically happen because you cover data inside the innermost loop. The innermost loop. Then, if you can cover the second outer loop, then you will see another performance bump because you give them enough cache space that they can cover multiple loops. That's why you see the cliff, right? So what you want here is if you know there's enough space to go around the second cliff, you should give them to the second cliff if there's benefit. But if that's not the case, just give them enough for the first cliff. That's where they gain more benefit. So this is what the performance cliff would look like. Something like this, right? So this is performance. And sorry about my handwriting. So this is the cliff. This is ways, right? The cache way. So if you give 1 or 2 way, you get improvement. If you give them 3 or 4 way, you see not as much improvement. And then if you can somehow cover the second loop, you see another bump again. And then not a lot of performance gain again. So what you want here is if you can give them this much, it's good. I mean, if you can, you want to give them that many ways. If you cannot, just give them this much. I mean, sorry. Eraser. Just give them around this much because there's no benefit in giving extra way until you see the second cliff, right? So that's the idea behind cache management around the performance cliff problem. You want to make sure if you have multiple applications, you give each application enough for that cliff. So the first idea is called cache partitioning. It ensures each application can only take n ways. And this n can be adjusted based on different phase of the program, right? In a program, there are multiple long running functions. So when you have each long running function, it will prefer certain number of ways. So you want your design to be able to adjust to new function calls in the program. What if there are a lot of applications and the associativity is say 8? It means that if you have 4 applications, you're not going to give each one of them just like 2 way, 2 way, 2 way, 2 ways, right? That's a little bit too small. Some ways can be shared among different applications. Some ways are going to be dedicated for certain applications. The benefit here is you reduce interference. You're guaranteeing some applications certain number of ways. They can use the cache, and you guarantee that you retain the benefit along the cliff, right? Any questions so far about the cache partitioning policy? So these are policies you can design, and you can basically pick a policy that you feel like it would work. Then you will run it on the simulator to see if it's actually worked. If it does work in reality, then you would actually try to have a sample ship. If this is like a real industry, then you have a sample ship to have the same policy and try it on a real program, then you would sell the ship, right? Any questions?
So in the cache partitioning, is there higher level than the cache block management in the lab?
Yes, yes. These are ways. These are ways. The associativity.
It's not the 8-way.
It's that 8-way thing. It's the 8-way thing. But you can build basically like you can modify the hardware such that it detects the application ID. and then ensure that that application doesn't use more than a certain amount of way. One way to do this in the real hardware is to basically say who can access way number 1, way number 2, way number 3. And you say, okay, application ID 10 can access way 1 and 2, things like that. There are multiple ways to implement it. I'm not well versed in the current version of the cache partitioning. This was like a pretty old topic. So I'm not sure if that's like a better way to implement it in the hardware, but I'm sure there are multiple methods to do this. There's a technique called set dueling, for example, which means that I'm gonna have multiple applications trying to use different number of ways, and we'll try to see who gets to use more from that benefit. Any more questions? Basically, these particular topics we cover in a lot more detail in the second semester class in advanced architecture, because this is a pretty important topic to talk about. Interference is a pretty important topic. So we talk into detail about different partitioning policy, different replacement policy, for example. So based on each application characteristics, you can use a different insertion or replacement policy. For example, you have streaming application. What is streaming application? It means that the application would go through arrays like A0, A1, A2, A3, A4, A5, right? Or A0, A2, A4, A6, A8, something that's predictable. So you can prefetch them so that when you need to access data, it's done quickly. But you will then want to kick that cache block out as soon as possible, as soon as you're done using, right? Because you use it once. If you want to prefetch, yeah, sure. And if you use it once, you throw it away, right? To actually try to increase the probability that you throw this cache block away, one thing you can do is prefetch, then keep them in the LRU. What will happen to your cache block if you keep them in the LRU position? If I have a LRU replacement policy, what will happen to that cache block? Okay, I'm not sure what my cat is answering, but she's trying something. So if you put your cache block in the LRU position, and I have an LRU replacement policy, what will happen to that cache block the next eviction? They'll get evicted, right? Because it's the LRU block. So if you prefetch and you keep them in the LRU position, that cache block get evicted. You might want to also find a way to detect hot and cold data. What do I mean by hot and cold data? Hot data get used often. So you can try to keep them in the cache. Don't bite my chin, please. And cold data are not used as often. You can evict them from the cache because it's used already, and you don't. That's less likely that they'll get used again, right? So you will try, the caching policy will try to retain the hot data. Any question about the cache replacement? I'm gonna just move on from this because we talked quite a lot about this cache replacement policy, including prefetching already. So the third idea was something that's a little bit more widespread outside of hardware as well. You can use something called victim cache, right? Victim cache means that you're going to have this like pseudo cache that store some cache blocks information that just got evicted. Why is that the case? Sometimes your cache block get unlucky. I'm going to have another access to this block soon, but because it's in the LRU position, I got evicted. So that future access never get to access this data from the cache. It's already get evicted to the main memory. So one thing you can do is you can use another like cache layer, but you don't store the data. You only store the tag. You're trying to detect, okay, any cache block that get evicted with future requests to that cache block. These are called the victim. The victim means that I got kicked out of my cache, but then there will be future accesses to this cache block. So you try to retain that information to ensure that this block is not evicted again, right? Because there's likelihood in the future that that block will have the same pattern. Why is there a likelihood something like that or something like these happen? Because your program in a lot of cases are run using for loop. You'll see the same exact pattern of data access because it's a for loop, right? Alternatively, instead of just storing the tag information, you can store the tag and the data and make the victim cache working like a fully functional cache. These techniques can be used in both the hardware cache and the software managed cache. Software cache can be things that are run, like for example, the proxy server is a software cache. So you can use these techniques to improve the cache performance. You get more hit rate because you can now detect who get evicted too soon. Any questions about the cache before we go into how to handle DRAM interference? So DRAM interference is another interesting problem because application can occupy more or less DRAM capacity, DRAM bandwidth, and DRAM priority in the scheduler. Right, so the first simplest thing we can do, because we can do cache partitioning, you can also do DRAM partitioning. It means that you can partition the channel, the bank, or the bandwidth. The bandwidth can be done virtually through the DRAM scheduler. The memory scheduler will try to detect, okay, which application have been scheduling for each of these all these requests, and they'll deprioritize some application if you have assigned more, basically more requests to DRAM from that same application. Partitioning the channel can be pretty simple depending on how you do it. This can be done in the OS. This is called page coloring. It allows some isolation between each application accesses. Any one of you heard about the newest NVIDIA card that they claim you can run, I think, seven applications in the cloud in parallel at the same time? My bet, because they never release what they are doing, but my bet, as far as I am concerned and as far as I have been reading papers, I have a gut feeling that they do this channel partitioning. They partition the memory channel in such a way that you can partition DRAM. And because I think, the reason I said I think, because I cannot confirm this, but I think NVIDIA, at least the most recent generation, use 3D stack memory. It comes with a lot of channel. So you can do channel partitioning in a really dynamic way, but it's still not as good as the CPU sharing that you can do in the CPU, right? So you still have some isolation. You can't fully utilize all your memory. The non-share channel or banks, as I said, when you can isolate them, it provides isolation from any other application because it has its own memory scheduler. So if you think about it, this non-share channel will see requests from one application. So you just do FRCFS. Whatever row hit comes in, like you just schedule row hit request first, simple and clean, right? You can partition DRAM capacity across different applications through page coloring. So if you're curious, feel free to Google this. You'll get a Wikipedia article that has a really good detail on how page coloring is done. Basically, the OS would set the bit that are the channel bit, right? You remember our memory mapping lecture in DRAM, there's a channel bit, there's bank bits, there's a row ID. The bit to the channel will be set by DOS. DOS will control where my request would go to. Why can DOS do this? DOS has a control over the mapping between virtual to physical address inside the kernel. Our second idea that you can do is DRAM scheduling. So this, I'm going to skip this part a little bit. I'm going to go through this relatively quickly because I've been through the scheduling, different ideas quite a bit, right? So memory scheduler can determine what application get prioritized, and you can ensure fairness running across different applications by first embedding application IDs to the memory request. When you look from the scheduler point of view and you see this request, you will maintain each of the application characteristics and schedule them based on these measured characteristics. The third thing that you have to do is the page management, because as I said earlier, DRAM is not just the interface between your processor and memory. It's also an interface between your memory and your storage system, which is hard drive and SSD. So when you are doing any paging, the OS will determine what data is stored in DRAM. This means I can control the application's data inside the memory, right? So you can make sure you avoid unnecessary page fault that takes a lot of time. Remember our talk that I did this year about this metadata, the virtual memory metadata. This is basically to improve the page management policy. You can utilize DRAM better with more information and making sure you don't run into a lot of page fault. You can, it allows you to utilize the memory limit much better, right? Then there's a problem of unpredictability. If you cannot tell how long each load or store would take, it means that you can't tell how long a function call takes. And you can't tell how long a program will take. It means that you can have a wide margin of error, and you can't narrow down that margin because you don't know how long data access can take. Some applications, however, have a hard deadline. So for these type of application, things like self-driving car or power grid or real-time embedded system, a lot of time what they do is whenever they have hard deadline application, that thread will be the only thread running on the machine. Any part that have sharing will not be shared. So make sure you finish that deadline. Why is that a bad idea? If you have multiprocessor, because utilization drop heavily, right? It would drop heavily to the point that why are you even having multiprocessor? Because you're running only one application, right? Another thing that is important with unpredictability is if you have a cluster machine and you want to give it to clients, right, and charge the clients money, the more you can share, the better. But if you have no way to predict how long the function would take, you cannot charge the client a lot of money. If you can tell and you can predict how long the function would take, then you can have a different cost model, right? If you want your application to be fast and guaranteed to finish within, say, 1 minute, you can pay more money. Otherwise, I won't give you that guarantee. It means that my application can be fast or slow based on the other application I'm sharing. So performance predictability is a really active area right now, given that everyone wants to use things like container, virtual machine, and real-time embedded system in self-driving car. If you can predict the performance, that basically would change the way scheduler can be done. So to provide lazy guarantee inside the hardware, one possible idea is to provide the worst case guarantee. But these are not good. As I said, these are active area right now. So these are really, really bad way to estimate the latency, right? So basically, this would allow the operating system to measure how long each program would take. But as I said, this is far from ideal. This is far from ideal. So keep in mind something that people have to work on. Any question before we go into cache coherency? Otherwise, we'll take a quick break because it's been an hour. So I don't want to like go into cache coherency for 1 more hour straight because I think you lose sanity. So let's do a 10-minute break. We'll meet again at 10:05. If you need coffee, go get your coffee. If you need sleep, I'm not sure you should go back to. But we'll meet again at 10:05. All right. right? Okay, so I assume most of you are back, if not all. So let's resume our discussion on cache coherency. Basically, this has to do with the fact that the same virtual address that you are writing in C, right? Whenever you need to access the data, they have to see the same copy of the data. It has to be the most updated version of the data. But with multiprocessor, as I said earlier, when you have shared cache, they are distributed across multiple cores inside the different processor. And this can be modified by multiple applications, right? So let's say you have two applications that want to read and write to the same cache line. These data might be in the private L1 cache as well, right? So it needs to make sure that reads and writes are coherent. So the question here is how can we maintain coherency across different cache? The high level idea is this. Basically, the high level idea is you want to tag the status of each cache line. If it's read only, our cores can access these data, and that's a good thing, right? Basically, you can access the data in parallel. You can guarantee that every single core will see the most updated version of the data. The problem comes when writes happen. If you have write to the cache line, this might modify the status of the cache line depending on the number of threads that writes on this same cache line, right? What do I mean by that? It means that sometimes I might need to send the update status to update the data on other cores' private cache. And this protocol is called the cache coherent protocol, which is the keyword here is the cache coherent protocol. It determines how you would update all your data. And the goal here, well, first of all, the goal has to be correctness. But for performance, when you have these protocol, it means that you are going to have to communicate between each private cache. So you want to minimize communication and data transfer, right? You want to increase the, you to not increase the latency of your read and not consume more power. These communication and data transfer would consume more power. It would make reads longer. Reads are important for your performance within the hardware because that's what stalls the pipeline. So cache coherent 101, basically, when you talk about the valid and invalid bits, this same concept applies. If I have a data in a private cache that is not the updated version, in this cache data, the processor would observe other process actions through a shared bus. This shared bus is called a Snoopy bus. Uh, it it is named Snoopy bus because it reflects the dog snooping around, right? When you if you have a dog, for example, you see that one of the main method for them to sense what's around them is to smell. That action is called Snoopy. Basically, to smell the area around themselves to make sure they know what's in the surrounding area. So this bus allows the processor to snoop around every other processor. So this is how you would visualizing this cache coherent let's say you have the update, right? So you have the update right here. Update, which is done by processor one. So processor one say, hey, I want to update this cache, this address, right? Then what you can do, what you need to do, to be honest, is you have this bus. So I'm going to use a different color in blue. This Snoopy bus between processor 1 and 2 that say, hey, I have update to the address. And based on the status of the processors to cache, if they have the same cache block, they will know that, okay, I have to invalidate this because I do not have the most updated copy of the cache, right? So then the question, as I said, the goal here is, well, if you're going to have to do this all the time, everything will get invalidated a lot, right? Because you have a lot of data access, right? The goal here is, can we do better? Can we do better in minimizing the communication? So one of the protocol you can do is called the MSI coherence protocol. Each cache block can have 3 states. Invalid, which is the cache line is not in the cache, right? You invalidate the cache line. Say, hey, I need to get this data from the shared cache. They can be modified. Modify means that this is the only copy and this copy is dirty. What does dirty mean? Dirty means that I write to the cache block. It doesn't mean that I cannot access the data. It means that I just write to the cache block, which means that if someone else wants to access this copy of data, this address, I need to flush. I need to make sure this writes propagate throughout the hierarchy, right? So the other state is share. Shares means that they can potentially have several copies around the private cache, but they are not modified. So if you have a read miss, you send a read request and you transition to a share state. Why? Well, basically, you bring the cache in, you're reading the data, so there's no update version of the data. Everyone who wants to read will have the transition to the share state. Write miss, send the read exclusive means that, hey, I just write to this cache block. So if anyone else has this address, basically invalidate yourself because you are not having the most updated version of the data anymore. And if a processor see the read exclusive, as I said, you invalidate yourself. When you send the read exclusive in the Snoopy bus protocol, inside the Snoopy bus, you transition to modified. You are the only one who owns the copy and you can use it. No one else can use it. Transition from share to modify can be done without reading data from the main memory. I originally share the data. I know that I write to the data, so I know that I am the only one who modified this data, so I can transition from S to M. The other processor will invalidate. So the problem is here. On a read, this go directly to share, right? On the read, this go directly to share. Even though this might be the only copy, right? If this is the only copy, what happened? Do you need to send the read exclusive at all if you are the only one who has this cache block? Yes or no?
No.
I cannot hear you, sorry.
You mean that the only one that has the cache block?
Yeah, let's say I have processor 1 and processor 2. and I read this cache block for the first time in processor 1. Processor 2 haven't even read to the cache block yet, right? So processor 1 will have the data, and it will be the only processor that has the data. It means that I don't even need to notify, right? I don't even need to notify processor 2. So on a read, you can go directly to ship. Well, you might want to have a different state because you don't want to send the read exclusive, right? So this can be done without notifying other caches. So the next protocol is called messy protocol. So this is like a textbook graduate level architecture cache coherent protocol, where each cache block, not just do MSI, you add exclusive state. It means that, well, as the exclusive name suggests, you have the only copy, but it's not a dirty cache block. So the difference between modified and exclusive is this. Modified means I have the only copy and I have updated this copy. The block is dirty. I need to tell everyone I have this updated version of the data. Exclusive means I am the only one who has the data, and this is not dirty. I haven't write to it. I just read from it. It means that if you want to transition from exclusive to modify, exclusive to modify, you don't have to notify anyone, right? Anyone, because, well, you are the only one who has the cache block. So basic cache coherent protocol has a lot to do with reads and writes, right? So read versus write, the difference here is write modify the data. So reads has to get the most correct updated version of the data. Key issues is first, you want to make sure if you need to read anything and that cache block is dirty from the other processor writes, you want to make sure the other processor writes get propagated to the hierarchy. This is called a flush. This is called a flush. So what you want to do is you want to minimize communication, and you want to only update if you need to. So it means that, as I said earlier, each cache block maintains the state MEFI. And there are two things to consider. What does the processor do? Do I read or do I write to cache block A? What do I see from the shared bus, the Snoopy bus? Anyone else reading or writing to cache block A so that I can update the status correctly? So let's go through an example. Right here are the two states. If I'm actually let me start with the exclusive state. Right. So if I don't have the cache block and no one else has the cache block, everyone is invalid. The first time that I read from and I have the copy of the cache block, I will stay here, right? So this is the notation I'm going to do. Processor read, processor write, Snoopy bus see a read, Snoopy bus see a write. So let's say I'm in the exclusive state and I'm doing processor read. I my own do a read to my cache block and I'm in the exclusive state. Processor read will stay at the same state, right? Because you're reading, you are the only one reading. What if I see Snoopy bus read? Where do I go from the exclusive? Snoopy bus read means someone else is trying to read the data that I own. Where do I go? Is it modify? Is it share? Or is it invalidate? No one modified the data yet, so definitely not modify. Right? there are more than one entity that has the data. So you are transitioning to a share. So if you see Snoopy bus read, you go to the share state. What if you have processor rights? Processor rights mean that, well, you are the only one who has the cache block. If you do a write, you go to modify because you are the only one who has a cache block, but you write to it. Now the cache block is dirty. Now the cache block is dirty. Is it possible to see a Snoopy bus write?
Is caused by another processor to write some.
Yeah, so if you see someone else is writing to this cache block, right, you no longer have the most updated copy. So what do you do?
Invalid. Just
you invalidate yourself, right? So if you have a Snoopy bus, right, you invalidate. You don't have the most updated copy anymore. You don't even own this. You need to basically try to get the most updated version of the data. All right, so let's say you're in the modifier state. You are the only one who owns the data and you have the rights. What do I do if I have a read? I stay here, right? I'm the only one who owns it. If I have the rights, I will also stay here. I'm the only one who owns it. It's already dirty. I write it again. It's going to be dirty again. What if I see a read? What if I see a read? I will go to share, right? I will go to share. Why do I go to the share state?
Because another.
Because I have the correct version of the data. So if I have a Snoopy bus read, I go to share. Do I have to do anything else? I need to flush. I need to get these updated data to everyone else. Means that I need to flush the data, flush it to the share cache, allowing everyone to say, hey, that's the updated data. If you want them, go take it. Right. So if you see someone else trying to read to this address, you transition to a share state and then you flush. The difference between M to S and E to S is whether you have to flush or not. E to S, no one updates the data, so you don't have to flush. Any questions so far?
So how do they ensure that it is the only one who have this data?
How do you ensure you are the only one who has the data? Typically that happens when you have rights. I am going to show it a bit soon. So the last thing is, what if I say, if I am gonna modify and I've seen someone write to the data. I go here, right? Invalidate myself. Say, hey, I can't use it anymore. All right, so that's when I'm in the modifier state. I'm gonna go do one at a time until the invalidate. So how about I'm in a share state? If I have processor read, I do this. I send processor read, stay here, right? Anything else? What if I do processor writes and I'm in a share state? I go back to modify. I'm the only one who has the copy, right? Everyone else would go to invalidate. If I have a share and I see the bus, if I see the bus, I'm in a share. If I see the bus right, I go to invalidate. If I see the bus read, I stay here. Right? No one modified yet, so it's safe for me to use the data. How about if I'm in an invalidated state? If I have a write, if I have a read, if I have a processor read, I'm the exclusive owner. Yay, I don't have to send any communication over. If I have a write, now I'm in a modify. I'm the only exclusive owner, but the cache block is dirty. If I'm in the invalidate and I see someone else is reading, doesn't matter, I don't care. If I'm in the invalidate and I see someone else writing, well, I'm already in the invalidate state, so I'll stay here. All right, so I'm going to use a different ink color to notify what do I have to send into the Snoopy bus when I do this transition. So the blue color is the bus signal. Right? The bus signals basically would send out, am I reading or am I writing? So if I'm transitioning from exclusive to modify, I don't have to send anything because I know I'm the only owner. If I am from the, I'm in exclusive, I'm going to share, I don't have to send anything as I said because I'm the only owner. If I'm in the modified state, I'm transitioning to share. I'm transitioning to share. Oh, no. If I have a processor read or write inside the modified state. If I have a processor read, I will send read, saying I have a read. Processor write, I'll send signal write, saying, hey, I modified the data. If you see this, modified it. If I'm in a share state and I have a write, where's the processor write? Over here, you send the write signal. If I'm in a share state and I have a read, do I have to send any signal? No, right? Because everyone else is in the share state as well for those who have shared. If I'm in the exclusive state and I do a read, I don't have to send anything because no one needs to listen to me. If I have an invalidate state, if I'm in an invalidate state, I'm reading, I want to send signal saying, oh, okay, if anyone else is in the share state, I'm the other entity that in a share state. So if I'm in a modified state or anything, I can either transition to share and flush or transition to, so if I'm in a share already, I stay at the share. If I'm in the exclusive and I see someone want to share the data, I transition to the share. If I'm in the invalidate state and I do processor writes, if I do processor writes, I will also send a signal saying, hey, I'm writing. To, no, my bad, processor write go to modify. If I have a processor write, I go to modify and I say, hey, everyone else, I now have the exclusive copy. So if you do anything, you then need to update your state. So that's complete the diagram. Any questions? So the blue thing are signal you have to send on the Snoopy bus. The red things are the state transition. Okay, so if there's no more question, let's go through some example from last year exam. So here is the question. Nope. I open it. Oh, here. Right here. So let me zoom out a little bit. So can you see the question from the screen? Let's see if they can do this and zoom. So can you guys see the questions? All right, so I'm gonna give you maybe 20 minutes and go through the question. After 20 minutes is over, I'm gonna go through this question with everyone here. All right. So basically, this question, we have 4 processors. Each processor, as I said, they have its own state. What that set, right, for that particular set, for each of the tasks, each one of them maintain a certain state. Then you, so these each of these box are for different cache block. Then you do load, store, store, load, load. Basically, read, write, write, read, read. Initially, is at the bottom. After you do these 5 writes, you see that the states are similar to what you see at the top. What is the initial state of your cache? So we'll spend, how about 20 minutes? Would that be okay? So this is a little bit of the reverse engineering. I really want you to practice this. After 20 minutes over, I'm going to go through the question with everyone here. All right. Okay, so I'm on the screen. Let me know if you have any questions. And to make sure you can speak, I'll mute my microphone so that you can freely speak whenever you want to ask questions. By the way, I'm not going anywhere. So if you have question, ask anytime that you have within the next 20 minutes so that we can go through the exercise in a more like fluid way. Actually, do you mind? Give me 5 minutes. I need to use the restroom. I'll be back in about 5 minutes. Sorry, guys. All right, I'm back. Any questions?
So I have some questions.
Yeah, so
So the cache zero
mhm.
mean that not only the processor zero can use that cache, right?
It's basically processor zero's own private cache. Think about it this way: this cache 0, cache 1, cache 2, and cache 3 are its own private cache. It just happened that some of these are shared. Well, all of these are shared data. So you want to make sure that if you sharing the data, you will have the most updated copy whenever you need to read or write to it.
Mm-hmm. Okay. Okay.
I'm trying to see if I can. I'm trying to see if I can put in the text. No, I'm not going to highlight the text. I'm going to edit the text too. Choose. Yes. Add the text box. So let's see if we can type this in. Okay, sure. Skip. All right, so let me go through this question one by one. So if you basically if you look at this cache state, right? One thing you would realize is it's only coming from processors 0, 1, and 2,
Mm-hmm.
right? It's only coming from processor 0, 1, and 2. Sorry, I forgot to turn on my video. So what you can then infer is if processor 0, 1, and 2 are original, at the end, everything is invalidated. So the first thing you can tell, the exclusive state at the end, right? At the end, you will then know this is going to be the same tag 0x13333, right? And this is the exclusive state because no one touched it. At the end, it's exclusive state. No one touched it. So it stays there. It stays there. One more thing. If you look at the memory instruction, right? I think the block size is 64 bytes. So you know, eight first byte is for the byte in block, right? And each processor is private to 56 bytes, right?
6.
And it's 4 byte addressable. So the byte in block is not byte addressable, it's 4 byte addressable. So you shift everything by 2 bits. You shift everything by 2 bits. There are 4 sets. This basically means that these the tag bits are essentially these bits. These are the tag bits. Why? Because you one cache block is 64 bytes, but you can't access every single byte. Oops. To highlight all this. So these are the tag bits. You need to access every single four byte chunks. So block of 64 is 8, shift right by 2, 6. Then the 2 more bits are the set index. So the last 2 bits, I'm going to use different color. So this thing is the set index, but the only top 2 bits, right? So let's figure out what set do they go to. So what is C?
Set 2 1 1 1 0 1 0, right?
1 0 1 0, right? So C1. No, I think it's 1 1 0 0. Isn't it?
1 0 0 A C D E F.
Yeah, I think it's 1 1 0 0. So the set index is 1 1. How about 8? 8 is 1 0 for sure, right? This is a set index. 4 is 0 0, no 0 1, and the set index for 0 is 0 0. The last one, the set index for 4 is 0 1. Any questions so far? These are the set that they go to for each of these 5 requests. All right, so let's do one at a time. Starting from R5, the last, because we are starting from the final state, the easiest way to go around this problem is start from the last request. Load to R5 is from processor 2, which is cache 2. To what set? Set number 1. To set number 1. So one thing you know is before this load, you don't know what's in here. It can be something. Basically, I'm loading this. The state can be M, E, S, or I, right? Because you don't, well, it can be other blocks. It can be the same old block. Doesn't matter, right? But you just read through it. What will happen to the other set 1? You see that, okay, they are all share for cache 0, right? They are share for cache 0. So initially processor 0, before this load instruction, it's likely the exclusive state, right? And you notice it's exclusive state because of the third load and store instruction. Store R3 0x1 FFFF40. It's the same address. That make cache 0 exclusive. No, actually that make cache 0 modified because it's stored. Basically, regardless of what state it was in, it's modified. And you can say, okay, before this memory instruction from P0, you don't know what's in here. M, E, S, and I, right? Because you don't know what's in there. I know my cat is next to my keyboard. Which means I have no idea initially what is cache 0 set 1. What is cache 0 set 1? One more thing. If you look at the first one, instruction from P1 that go to set 3, you will see that it's a load instruction, and at the end is load from P1. So that's basically cache 1. You are the exclusive owner, right? Because if you look at cache 1 set 3, you are the only exclusive owner. So you don't know before this, I don't know what's in there. Again, MESI, everything is possible. I might be loading this new block. I might be having the exclusive state earlier. But what I will know is that for every other caches for set 3, they should have the same state as earlier, as a final state. So that should be the same thing here, and it's invalidated because you know that somehow everything looks the same. So this is modified, it's the same state as earlier, and this same thing as well, 0x10 FFFF, invalidate, because you know that first load move cache 1 into the exclusive state. The only way that can happen is if the final state looks some way, it's definitely not in the shared state. So if they're already in an invalidated state, stay there. If they're in a modified state, stay there. If you are if you're in a modified state, but it's a different tag, notice that it's a different tag. So if I highlight this, the tag is different. It's a totally different cache block. Stay there. Again, different cache block. Stay there. There's no modification to set 3 to the same tag. The only one that has the same tag is cache 0. Cache 0 is already invalidated, so you know before this is also invalidated. Let's wrap up the access to this one, to set 0, right? There's only one request to tag one FFFFF to set 0. So if you see anything that's not one FFFF, you will then be able to copy. As I said, I already copied that to 0x13333. Over here, you see 0x10 FFFF, so you know that, hey, there's nothing to do with this particular tag. So you can copy it over. 0x, what is it? 10 FFFF. And this is invalidated. You have one access to R4 to one FFFF. Somehow both of these are shared. Is an access from processor 1, so you don't know what processor 1 had in the beginning because you just changed the state through that access. But you know that processor 0 will have the same tag, which is 0f1ffff. And because it moved to share, you can move to share from modified, you can move to share from exclusive, and you can move to share from the share state. As long as it's not invalidated, this is legit. If it's invalidated and someone read from it, you don't have to stay, you stay at the invalidated state, but now you are in the share state. It means that you own this copy or you share the copy. Right? Then let's do set 2, the second instruction, store R2 0x1100 to set 2. So let's finish up set 2. Anything that's not tagged 0x110000 stay the same. What are those? These requests to 0x10FFFF stay the same because it has nothing to do with this load at all. Modify. Set 2 is 0x0, right? Also has nothing to do with that load at all because it's totally different tag. So I can copy it over. Now let's go to 2 in the cache 0 and cache 1. The load the load is to from cache 1, and you see that it's in the modified state, right? It's in the modified state. So you know, and over here is invalidated, right? It's invalidated, and that request is a write. So one thing you know is for sure this set to cache 0 is 0x1 what is it? 0x11000, because it's the same tag, but the state has to be well, it can be anything because someone write to it, so I have to invalidate myself. Before this, it can be anything. Over here in cache 1, it might be a different tag, but I have a right to this particular tag, so I can put in MPS and all right. So the last thing I have to do, is any modification to tag 1. Tag 1, there are 2 requests. Originally, there's a store request to R3 and load request to R5. Both of the tag are 1FFFFF. So if you look at set 1 over here on top, you see that the tag is different. So I do the same thing again. I say, okay, this has nothing to do with these 2 requests. I'm going to write it here, 0x000, and invalidate, right? And the last box that I had to fill in is set 1 for processor 1. Set 1 for processor 1. And because you see that it's also 0x1 FFFF, but you invalidate it, it means that that write to R3 would have invalidated, and then you follow it by a read to R5, right? So over here you will know is, well, has to be this tag 0x1 FFFF, but you don't know what state it might be in. So this can be M or E or S or I. So this complete the question. Any question from this exercise? So I will save. Well, actually, I'll just send you the PDF with the solution.
So the X mean that it may be some different tags.
X means that it can be a totally different tag. It can be the same tag. I don't know what the tag is because I have a cache access to that set that replaced the old block. Right? It replaced the old block. That's why I need to put an X, because before I access, let's say I do load R1 0x1, what the first access to P1 cache. That is to set 3, right? To cache 1 set 3. Before I do this load, I have no way to guarantee what's in my cache, because that particular load just block. That's why I put in an X, because I have no way to tell.
So when the direct map cache mean that.
So this is 4-way cache. No. This is direct map cache. My bad. This is the direct map cache. It means that there's only one way. If you have cache access to that way, it replaces the old block. Replace the old block. So it's direct map cache with 4 ways. That's set associative. No, sorry. It's direct map cache 1-way set associative 4 sets. 4 sets. So the set ID is from bit 7 and bit 6. So those are the set ID from your address. That would tell you where the access is going. All right, so if there's no more question, we will go back to our lecture. So that was the example from last year exam. So any questions similar to this, it's fair game. Good thing, it's fair game. Another policy, which I'm not gonna talk about too much in detail, it will be covered more in detail in the next advanced architecture class, is it's called directory-based protocol. But instead of using a Snoopy bus, you use a central directory to keep track of copies of cache blocks, right? So the policy is simpler. The policy is simpler. For each cache block, you store n plus 1 bits. 1 bit per local cache, basically. If it's a value 1, it means that the cache block is in the cache, and the 1 extra bit is for the exclusive bit. When you have the read, you set the bit. When you have the write, you invalidate everything else in the table to reset the directory. The cache can now update silently if the exclusive bit is set, but the communication between the processor and the directory can be an issue because every single private cache has to consult the directory. So that's it for data coherency. Any questions so far before we move on to data coherency? I mean consistency. All right. So the last thing we are going to cover today is how to ensure data consistency. The last bullet point, I'm going to basically migrate to the next lecture. So if you talk of memory consistency, it's basically talking about when you have multiple applications that share the data, the order of read and writes are important. And this is actually specified by the ISA. The ISA will tell you how to ensure consistency by what policy. The ISA will tell this is the order I expected. So please design the hardware to follow this particular order. On a single processor, this is simple, right? In a single processor, you have data load, data store. It just has to follow the same order, right? We cover this in our order execution by making sure you have the reorder buffer and the write back. Ensure that you have like a sequential way to modify all the register files and the memory. If you use data flow model, which is something like out of order processor, the dependency determine the ordering, right? The ordering will go based on the dependency that you measure. Sorry, let me draw cat's toy so that she is not climbing my keyboard. Memory consistency is basically one of the major issue, to be honest, in multi-core processor, because threads should not update the shared data concurrently. They are protected in the critical section, and you have synchronization to basically construct and protect this synchronization point or the critical section to log semaphore or conditional variables. And the multi-core should provide the correct execution based on this synchronization primitive. Basically, the programmer write the code this way, your hardware is supposed to follow the exact same semantics that the programmer is giving you. Don't modify the program's code unless the programmer tells the hardware this is what they need, right? This is a big assumption, assuming the programmer know what they're doing, which in many cases, if you write multi-threaded program, they sometimes don't know what they're doing. Sometimes they forget to lock, sometimes they forget to unlock. So this problem can blow up, especially if you don't know how to program things in parallel, which is one of the important skills that many advanced engineers should know. So what do I mean by sequential consistency? This is basically defined by one of these really high impact paper by Leslie Lamport. Leslie Lamport is one of the computer scientists who got the Turing Award. Basically, that's like a Nobel Prize for computer scientists. That's the highest award that anyone can get in our area. It is basically as equal to getting a Nobel Prize. So that's how important this particular work is. So Lamport actually not just doing this work, but he has multiple works on this topic on how to ensure things like consistency and synchronization. But the paper that is defining the sequential consistency is in 1979. The paper is called How to Make a Multiprocessor Computer That Correctly Execute Multiprocess Program. You can guess from the title, it has a lot to do with correctness. It has to do with the correct order of things. It has to do with multiprocessor. Multiprocessor is sequentially consistent if the result of any execution is as same as if the operations of all the processor were executed in some sequential order, and so both the bullet point has to be true. The operations of each individual processor would appear. I stress on the word appear because that's important, in this sequence, in the order specified by its program. Basically, it means that if I specify the program to have this order, you want to make sure the processor see and modify data in the same sequential order. This is the memory ordering model, and typically this is specified by the ISA. If you take the ISA and implement your hardware, you need to follow this. If you don't follow this, the programmer will say, what the heck? Because I expect this sequential consistency specified by the ISA, but the hardware does not. So here are some examples. Let's say I have 4 operations, A, B, C, and D. If you look at global ordering, any permutation of these can be correct. It can be A, B, C, D, A, B, D, C, A, C, B, D, B, C, A, D, right? The actual observed order depends on the implementation and the dynamic latency. As I said, any permutation of these load or store, basically these operations, can be correct global ordering, but the processors inside the multiprocessor has to see the same sequential order, the same order. The benefit is our processor as well see the same ordering. So if it's BADC, every processor would see BADC, right? Not one processor BC. It's not the case that processor 1 see ABCD, processor 2 see ACBD, processor 3 sees BCBA. That's not sequent. It is not consistent. Sequential consistency means whatever the processor see, every single processor see the same sequence of operation. It means that there's no correctness issue due to processors seeing different pieces of data. However, across different execution of your program, different global ordering can still happen, which means that this is going to be really difficult to debug, because let's say you run it for the first time. I see ABCD. Every process see ABCD. But the bug happened. Let's assume that the bug happened if you somehow do ACBD. What's the likelihood if I give each operation equal chance and I'll get A, B, D, C? What's the likelihood of that happening? 1/4 factorial, right? So it's 1/24. You need to run the program 24 times. That's the expected value that you see the bug once. So you can imagine in a parallel programming world, debugging is a big topic because it can be difficult to debug because those are bugs in your program. The downside of sequential ordering is, well, having the global ordering is a really strong guarantee. Why? Let's say you have 1,000 operations. Global ordering means that every single processor sees the same sequence of those 1,000 operations. Do we always need global ordering? And how often does the critical section actually modify the shared data? That's important, because if you don't modify the data, you're good, right? You can read the data, nothing is modified, it's the same sequence of data. So what if you make relax the policy, saying, hey, instead of doing global ordering on all operations, I just look at writes, right? I just look at writes, and I implement what we call total store order memory model. It means that, well, I just need to make sure the write happen in the same sequence, right? Or what if we enforce global ordering only at boundary of synchronization, the barrier, making sure the program enter and exit critical section with global ordering? This is called relaxed consistency model. You don't have global ordering when you don't have sharing. I don't care how I see the others process data because I don't share that data. I only care before I enter critical section and exit critical section when I actually need to use the shared data, right? So this is the relaxed consistency model. You get better performance and you're still correct. A weak consistency model is when, well, ordering is important when the operation affects the shared data. That's why it's called weak consistency model. The idea is the programmer, your job to specify the non-shared region. This is done through memory fence. There's a memory operations that fence, basically it fence out non-shared region. Memory operation before the fence must complete before you start things in the fence. Memory operation after the fence must wait for the fence to complete. The fence complete in program order. So synchronization operation acts like a fence. Barrier, wait, spin lock, all these things acts like a fence. The downside, your job to program this. Basically, you need to make sure it's correct. So that's the downside. That's it for the consistency model. It's a little bit brief because I have two choices. Basically, I can make it really long, which will run out of time, or make it more brief. If you're interested in this consistency model, I'm going to go into more detail in the advanced ComArch. Basically, the reason I repeatedly saying this.
To not my connection, right?
I can still hear you.
Okay.
So,
yeah.
All right, awesome. Am I still recording? Okay, good. My cat doesn't walk on my keyboard. He walk on the power at like the power switch, so she turned off everything. Yeah, but I'm back. Sorry, guys. So let me. Do you see my screen? And you still see before we leave today?
Yeah.
yeah.
Okay, cool. All right, so basically that's the end of the lecture content. So let me first stop the recording in order to make sure it doesn't mess up.